Next, let's look at a few examples of integration by parts. So our first example is the integral of x sine of 2x dx. So like we did in our introductory video on integration by parts, we're going to set u is equal to x, and then dv will be sine of 2x times dx. Right, because we set u to be a power of x if we can, because powers of x eventually differentiate down to 0. They become, you get lower and lower powers, so you want to take the derivative of u, and then you can take the integral of the other guy. So du is just going to equal dx, and then v, so we need to compute the antiderivative of sine of 2x. Well, the derivative of cosine is minus sine, so the antiderivative of sine is going to be minus cosine of 2x over 2, so divided by the derivative of the inside. Major minor method or substitution method. Major minor method really is an example of substitution, but sometimes you don't have to go through the whole process of the substitution method to see what to do. You just divide by the 2. And you can check in your head, derivative of cosine of 2x is negative sine of 2x, so that cancels, times the derivative of the inside, which is 2, which will cancel down here. So this one's going to equal uv, right? So it's uv minus the integral of v du. So it's going to equal u times v, which is minus x cosine of 2x over 2, and then minus the integral of v du. It's minus, and we have an extra minus sign here, so it's plus the integral of cosine of 2x over 2 dx. So for our answer, we get minus x cosine 2x over 2, and then plus the integral, or the antiderivative of cosine is sine, so we get plus sine of 2x over 4, plus c. Right, so again, we want to divide by the derivative of the inside, antiderivative of cosine of 2x, sine of 2x divided by 2, so we get 1 over 4. So that is the integral of x sine of 2x. So not too bad. Let's do another example. Let's do the integral of x squared e to the 3x dx. So here we're going to have to use integration by part twice because we have x squared. So we'll start off by saying, well, u is equal to x squared, and dv is equal to e to the 3x dx. So our u is right here, and then our dv is right there. So, okay, so we have u and dv, so next we need our du. du is going to be 2x dx, and then v is going to be 1/3 e to the 3x. Right. So this is equal to uv, so that's x squared e to the 3x over 3, and then minus the integral of v du. So for the coefficients, we get 2 times 1/3, so minus 2/3 integral of x e to the 3x dx, like that. So u, so this was our u right here, and then this one was v, right? So that's the antiderivative of e to the 3x, and then minus v du. So there's the v, and then there and there, it's the du. And the 2 and the 3 also belong in there as well. So, okay, well, that's nice. We have uv minus the integral of v du, and so we started off with an integral of x squared times e to the 3x, and we get something, minus 2/3 times the integral of x e to the 3x. So we've reduced the x squared e to the 3x to an integral of x e to the 3x, and to do that one, we have to use integration by parts again. So the integral of x e to the 3x dx. So we'll do integration by parts. So here our u is equal to the x, the dv again is e to the 3x dx, our du is just dx, and our v is 1/3 e to the 3x. So when we do integration by parts here, we get uv, so that's x e to the 3x over 3, and then minus the integral of v du, so that's minus 1/3 integral e to the 3x dx. Now the integral of e to the 3x is just e to the 3x over 3. So this whole thing is going to equal x e to the 3x over 3 minus e to the 3x over 9. So that's exactly the integral we have right up here. So we want to take this answer and plug it in for that integral right up there. So in the end, we get the integral of x squared e to the 3x dx. So starting up here is equal to this, x squared e to the 3x over 3, and then minus 2/3 times this. So minus 2/3 times this is minus 2x e to the 3x over 9, and then minus the negative, so that becomes plus 2/3 times this, 2 e to the 3x. 3 times 9 is 27, and then plus c. So our integral of x squared e to the 3x is x squared e to the 3x over 3 minus 2/9 x e to the 3x plus 2 over 27 e to the 3x plus c. So there's the integral obtained easily and readily using integration by parts. So those are two simple examples using x or x squared as the u. So for our next example, we have something that at first doesn't look like it's an integration by parts problem at all. What's the antiderivative of ln of x? Well, you first think, well, maybe substitution, but you need a 1 over x to make the ln of x a u. So substitution doesn't work. So how do we find the antiderivative of ln of x? I mean, it seems to be one of our basic functions, and yet there's no obvious antiderivative. We don't know of any function that when we take its derivative, we just get ln of x. But we can use integration by parts. And the trick is, well, I know how to take the derivative of ln of x. So what if we did that? What if we did something a little bit different than we have been doing? What if we set u is equal to the ln of x? Because I know how to take the derivative of that. You might be thinking, okay, if it's integration by parts, shouldn't ln of x be dv? But remember, dv is something that you have to know how to compute its antiderivative. So if you already know the antiderivative of ln of x, you don't need to do anything to find the antiderivative of ln of x. So the ln of x should not go for the dv, because after all, that's what we're trying to find out. So the idea was, well, let's just see what happens. And this is how things are discovered. People just play with the equations and they play with mathematics, and once in a while you just figure something out that works, and then you tell everybody about it, and then they told me and I'm telling you. So never be afraid to see where paths take you in mathematics. You have an idea, see if it works. Follow the steps and see if it brings you anywhere. So somebody was thinking, well, what if we set u is equal to ln of x? Well, what would the dv be? Well, the dv has to be just the dx. So here u is right here, and then the dv is the dx. Okay, well, the du is then 1 over x dx, right, because the derivative of ln of x is 1 over x. And then v would equal x, right, because the integral of 1 is x. Okay, so let's see if we got anywhere. So it's equal to uv, so that's x ln of x minus the integral of v du. Now v du is x times 1 over x times dx. X times 1 over x is just 1, so it's minus the integral of dx. So we did get somewhere. So in the end, we showed that the integral of ln of x is equal to x ln of x minus x plus c. Right, because the integral of dx is just x. And there's the formula for the integral of ln of x. Now, if you're skeptical, well, let's check. And you should always check your answers. So let's take the derivative of the right-hand side. So the derivative of x ln of x minus x. Okay, for this first one, we're going to need the product rule. So it's the first times the derivative of the second. So it's x times the derivative of ln of x, which is 1 over x, and then plus the second times the derivative of the first, which is 1. So that all comes from x ln of x, and we get these guys. And then minus x, derivative of minus x is minus 1. So, and then this whole thing simplifies. X times 1 over x is 1, then plus 1 times ln of x is ln of x, and then minus 1. So 1 plus ln of x minus 1 is just equal to ln of x. So the antiderivative of x, or the antiderivative of ln of x, truly is x ln of x minus x, and it works. And then finally, we have another important example, the integral of e to the x sine of x dx. So this is the integral of an exponential times a sine. Now you can get a little bit more fancy, and I encourage you to do this on your own for practice. Instead of having e to the x, do e to the ax, where a is an arbitrary parameter. And then instead of sine of x, do sine of bx, where b is another arbitrary parameter. So treat a and b as constants and do the integral e to the ax times sine of bx and see if you can work that one out. The steps are the same, but I'll just do this slightly simpler case so you can see how the trick works. And then do the same thing replacing sine with cosine. Okay, well this is an integration by parts, or you would think integration by parts because there's no substitution that we could do that would make this easier. And we have a product of two functions in the integrand. Now the question though is, do you make you set u is equal to e to the x, or do you set u is equal to sine of x? And for this particular problem, there's no wrong answer. So let's just set u is equal to e to the x and dv as sine of x dx. If you want to do it the other way, I encourage you to do it the other way on your own and just see where it takes you. You'll get to the same answer in the end. In fact, it doesn't matter. Setting u is equal to sine of x might even be easier because you're just taking the derivative of the sine or the cosine instead of integrating it. But we'll practice thinking about antiderivatives of sine and cosine. And the first time somebody did this, they didn't know what was right, so they tried something. So they said, there's the u and there's the dv. And then they went back and said, well, what happens if we try the other way? And they get the same answer. So u is equal to e to the x, so du is equal to e to the x dx. Now dv was equal to sine of x dx, so v is equal to minus cosine of x, because the derivative of cosine is minus sine. Remember, we're going backwards. Derivative of cosine is minus sine, so the integral of sine is minus cosine. Okay, so we get, again, we have this kind of backwards check. uv minus the integral of v du. So uv is minus e to the x cosine of x, and then minus the integral of v du. We have a minus sign in here, so I'm going to put that right there. And then we have e to the x cosine of x dx. Well, that doesn't seem to help. We started with the integral of e to the x sine of x, and we ended up with something plus the integral of e to the x cosine of x. It doesn't seem to be getting any easier. But somewhere someone once thought, well, let's try it again. Let's just keep, don't have anything better to do, you give your thoughts a try. So what if we were to do integration by parts on e to the x cosine of x? So let's now look at that integral. So let's look at the integral of e to the x cosine of x. It doesn't seem very hopeful, but let's just give it a whirl and see what comes of it. Okay, so let's set up u is equal to e to the x, dv is cosine of x dx. Now for the second time around, try this on your own. Use the opposite. For u, this time use cosine of x, and for the dv, try e to the x dx. So we did it using e to the x as u the first time. For this integral, try using the e to the x for the dv. See what happens. So switch them on the second step. What happens is that there is a correct, the first time when we did this and we set up u and dv, it didn't matter which was which. But now that we set u as the e to the x, we want to use the same u here. We want to use the e to the x again. If we had set u is equal to sine of x, here we would be setting u is equal to the cosine of x. Right? So we want to keep them the same, because when you so I mentioned I encourage you to switch them. Try u is equal to cosine of x and dv is equal to e to the x dx. What happens is when you switch them, you undo the step. So if I use u is equal to cosine of x and dv is equal to e to the x, what you get here is going to be e to the x cosine of x, which will cancel this one out, and then plus the integral of e to the x sine of x. So in the end, you just end up with the integral of e to the x sine of x is equal to the integral of e to the x sine of x. So when you switch, either the exponential or the trig function, when you switch them on the second step, you're actually undoing the first step. So the upshot is you want to stay consistent. We used e to the x as a u before. Let's use e to the x as a u this time. If you don't do it the same way, you're undoing the first step and you just get something that doesn't help you out at all. Go through the calculation and show that, and you'll see what I'm talking about. So u is equal to e to the x because that was the same way we had it set up before. This is for the second integral, this one up here. So then du is equal to e to the x dx, and v is equal to sine of x. Right? The integral of cosine is sine because the derivative of sine is cosine. Okay, so this one is equal to uv e to the x sine of x minus the integral of v du. So minus the integral of e to the x sine of x dx. So this piece right here is what that integral is equal to. Again, it doesn't seem useful because, hey, this is the integral e to the x sine of x, which is what we're trying to find out to begin with. We're just going in circles here. But let's substitute this thing into here and just see what comes of it. See what happens. Remember, all this stuff was figured out, discovered in the 1700s, 1600s. This is what people did. They sat around and tried stuff like this. So this integral, starting back from the beginning, the integral of e to the x sine of x dx is equal to this minus e to the x cosine of x plus the integral of e to the x cosine of x, which we said was equal to all of this. So I'm going to add all of this. So plus e to the x sine of x, and then minus the integral of e to the x sine of x dx. Now take a close look at this equation. Just kind of let it, pause the video and let it, take a look at it and say, did we get anywhere, or is this completely futile? Are we going anywhere with this? How many more times do we have to do integration by parts to get the answer? This is what we're trying to find out, this integral right here. But by doing integration by parts twice, we came up with this integral again on the right-hand side with a minus sign. So what if we treated this like an algebraic equation? Remember in the good old days when your biggest worries were to solve for x, and somebody told you 3x plus 7 is equal to 20, find x? Well, it's the same deal because this is our unknown. So our unknown is just this integral right here, which has just some value, it's equal to something. And here's the negative of it. So what if we take this and add e to the x, or the integral of e to the x sine of x to both sides? Well, if I add the integral of e to the x sine of x to the right-hand side, that's going to cancel out with this one. If I add it to the left-hand side, I'm going to get two of them. So this equation is the same as 2 integral e to the x sine of x dx is equal to, okay, I'm also going to switch the ordering of these two. So I'm going to write this one first. E to the x sine of x minus e to the x cosine of x. I switched the ordering because instead of having negative a plus b, I'm just doing b minus a. Right? It's just kind of a style thing. So these two terms are right here. And I basically took this and added it to both sides. So I added this one, moved it over to the left-hand side. So now I have two of them. Now, to finish it off, the integral of e to the x sine of x dx, all we have to do is divide by 2. And I'm also going to factor out an e to the x just for good measure. It's e to the x times sine of x minus cosine of x divided by 2. And then we need the plus c. So the integral of e to the x sine of x dx is e to the x times the quantity sine of x minus cosine of x all over 2. So pretty powerful formula, integral u dv equals uv minus the integral of v du. You probably, leave yourself, lock yourself in the room for the weekend with a bunch of paper, maybe some markers and a white wall, and try to intuit that the antiderivative for e to the x sine of x is equal to this stuff. It's probably not so obvious, right? But this technique allows us to get to this kind of complex answer using just relatively straightforward, simple, direct steps. You just do that, and you get this. The only kink in this example is you have to do it twice. So you have to sit down and do it a second time. But you get a pretty, non-intuitive, you probably wouldn't have just sat down and guessed that this was the antiderivative of e to the x sine of x. But it is. And you can check, I encourage you to check at home as always. Use the product rule on this one and show that you get just e to the x times sine of x.